All right, so we'll continue discussing some problems, but these problems will be from the tutorial sheet number 10, the last tutorial sheet. Okay, so this is the first problem. We have a coiled spring which has, it is shown here as 4 coils, but in general, let there be n coils. And it is made of a material having a shear modulus of G. And we are required to determine the stretch of the spring when it is subjected to the load P. So it is stretched on two ends by this force P, and in response to this load, we are required to find out the stretch in the spring. And one simplifying assumption is that the coils are supposed to be, we can consider them to be so close to each other that for all intents and purposes, this angle theta inclination, this helical angle, that is equal to approximately 0. And the deflection is caused entirely by the torsional stress in the coil. Okay, so you may have some shear stresses and such other things, but the transverse shear and those things, but those are going to be completely neglected. So tell me how I should proceed here. We are supposed to find out the deflections, the stretch of this spring, how much it is stretching in this axial direction. Please suggest something.
So will be PR.
Yes, torque will be PR. Very good. So we have already done a similar problem in one of the earlier tutorial sheets. So we know that the torque is equal to PR. If you take a cut section anywhere along this spring, you will find that this P is contributing with this moment arm R a torque PR. What else? What is the next thing that we can do? So using energy methods, of course. So here it is a case of torsion, and we do have an expression of the strain energy associated with torsion. Okay, so the general formula is for a beam 0 to L T square by twice Gj. So this is for a beam, but suppose this torque were a constant along the beam, then this would just be equal to T square L by twice Gj, where L is the length of the beam. Now this coil, it can also be considered to be like a beam, like a curved beam. So yesterday we were discussing problems involving curved beams, and we had said that if the radius of curvature is considerably larger than the depth of the beam, then so I'm referring to this particular problem. So if the radius of curvature is considerably larger than the depth of the beam, then even though this is curved, this may be considered using the same kind of formulas that we have learned for beams. So in our particular case here, the depth is given by this diameter, and this capital R, it is evidently much larger than this D. So these are the kinds of simplifying engineering assumptions which we are allowed to take. And if we do that, then we can directly apply this thing. The only problem is, what is this L? So any ideas?
So number of turns into circumference.
Number of turns into circumference. Yes, that is the thing. And that kind of an idea works only because we have been given this simplifying assumption that theta is approximately equal to 0 degrees. Okay, so if the spring were like this, okay, it were like this, something like that, then such an approximation would not be very valid. Okay, however, the coils are very, very closely spaced, so that for all intents and purposes, that theta, the helical angle, that is just 0. So length of this coiled beam, so to speak, is nothing but, so L will be equal to twice pi r, which is the circumference, times the number of coils. Okay, so we have this expression. T can also be substituted by PR. So we have this thing, P square R square twice pi R N twice Gj. And all we have to do to find out the deflection is just do this thing. Sorry, right, this one. So please do this and substitute for the for this expression of j. You please substitute this as pi small d to the power 4 by 32. So what we are basically using is that half of pi r to the power 4. So please substitute this thing. Yes.
So I'm not able to get how the torsion is coming out to be PR.
You refer to the previous lecture that we had. We had quite a bit of discussion about that. Okay, someone actually asked something, and in that response also I said something. You please refer to that, okay? I want to go forward with the problems here because that thing is not directly related to the energy methods per se, okay? That had to do with the previous thing. So please substitute the values and check if you're getting this answer.
Yes, sir. We are getting this.
You're getting, right? So let's proceed. I mean, it will come, okay? I mean, just a matter of properly substitution. Okay, so this next problem, I want to have a little bit of a discussion associated with it. I don't intend to actually come down to the numbers and actually solve and get the answers. Rather, what I think is more important is to discuss the ideas behind the solution. So we have a beam AB, and this beam AB, it has a square cross section, 100 mm by 100 mm. Now this CD, it's a bar, and it has a diameter of 10 millimeter. Okay, so it's kind of just supporting this beam. If both members are made of steel, so both the beam and the bar are made of steel, determine the vertical displacement of the point B and the slope at point A. So basically there are two problems hidden here, included here. One is the question associated with what is the deflection here. The other is the question associated with the slope here. Okay, so but even before we begin writing down any formula or anything, you tell me whether this structure is statically determinate or indeterminate. My question is whether whether the structure is statically determinate or indeterminate. Somebody said something.
Sir, it's statically determinate.
It is statically determinate, okay. So for instance, one may be tempted to think that this is almost like a cantilever beam and this is like a redundant support. But that is not really true, because a cantilever beam would not have a pinned support at the wall. Rather, it would be clamped to the wall. So here, if we did not have this support, this beam would not be remaining horizontal like this, it will be swinging down like that. Okay, it would not be a stable structure. So we do need this bar to support this in this horizontal position. This bar is not a redundant support. So that is one way of looking at it. If you want to be very formal, the best way actually to ensure that a structure is indeed statically determinate or indeterminate is to actually identify the unknowns, the number of the unknowns, and compare that with the number of static equilibrium equations, which are of course going to be always 3 in number. 3 in number in the sense that we are always going to have not more than 3 independent equations from the considerations of static equilibrium. Okay, you can write any number of equations, of course, considering moments about various points, but only 3 of them are going to be independent. Okay, now that you have identified that this structure is statically determinate, at least we do not have to worry about some reaction forces remaining undetermined. So using statics, we can actually determine all the reaction forces everywhere. But the question is not about that. The question is actually we have to first find out the displacement at the point B. Now, in all the previous example problems, we have been using Castigliano's theorem. Now, just for a change, let us go back to the principle of virtual work and consider if it may be possible to solve this problem using that. So, considering principle of virtual work, tell me how I should proceed. So, principle of virtual work, how I should proceed, just the general steps. If I intend to find out the displacement of the point B or the deflection at the point B in this downward direction itself, what should I do? So let us quickly jump back to that previous slide where we had where we had discussed the principle of virtual work. So this one. Okay, so remember we had stated these algorithmic steps, and at the end I had written this thing that on the left hand side you write the virtual force, which will be ultimately set to be equal to 1 in magnitude. Whether this is actually a force or a virtual moment, its magnitude we are going to set equal to 1. If it is a force, it is going to be multiplied with the actual deflection due to the real forces at that point of interest. If we are using this as a virtual moment, then it is going to be multiplied with the corresponding angle representing the slope at that point of interest, but measured in radians. On the right hand side, we have, through this sigma representation, what we mean to say is that whatever we write here, it is for the entire structure, whether it is a truss or a beam or whatever structure it is for the entire structure. And this delta F are the internal virtual forces that are generated in response to this externally applied virtual force delta P. Okay, so any structure you take, you remove all the actually applied loadings and just consider that structure, apply the virtual force, and when you apply that virtual force, through again the use of statics, you can determine all the internal forces or the internal moments. So those are these represented by this delta F. And these are going to be multiplied with the deflections represented by this U, but these are the deflections associated with the real forces. So through this little discussion, I wanted to briefly recap what we had discussed at the end of these algorithmic steps of applying the principle of virtual work. Now let us get back to the problem, and in light of this refresher, you tell me what I should do. I intend to determine the displacement at the point B. So this is our point of interest, and the direction of interest is in the vertical direction. So following our algorithmic, all that we need to do is apply a virtual force of unit magnitude in this direction. So something like this. Okay, we will apply our delta P here. This delta P, of course, is going to be equal to 1 Newton, okay, or 1 kilonewton, something like that. Please remember that when I am applying this delta P, I am not considering the existence of this 10 kilonewton, because that was the first step of our algorithm that we remove all the external loading, and on that unloaded body we apply the virtual force of unit magnitude or the virtual moment of unit magnitude. Here we are interested in the deflection, that is why we are applying the virtual force of unit magnitude. Now, you know very well that, so suppose I had asked you to consider the original problem itself, this where this 10 kilonewton force was applied, you would have been quite comfortable determining the forces anywhere within this structure. First of all, you would have determined the reaction forces, the force here, and then if I had asked you to determine the shear force anywhere along the beam, you would have immediately been able to do it. Okay. Now, is the situation any different now that we have removed 10 kilonewton, this 10 kilonewton force, and instead of that, I am applying this delta P? Situation is exactly the same as far as the statical mechanics is concerned. Okay, so when you apply the delta P, remove the loading, remove the external loading, and apply delta P. Now this delta P will generate some internal forces, some internal reactions, whatever. Okay, so internal, fine. So you have to actually do that problem. Okay, you have to consider this kind of this entire thing you have to do actually. Okay, there is no getting away from this. You have to do it. So, okay, so you have to solve for the internal forces. Now, once you solve for the internal forces, if we quickly write down here that general expression, we have delta P, del P into delta is equal to sigma delta F into U. So this delta P is known. In response to that, we have just determined the delta F. Okay, rather we have determined the delta F's at wherever we wish to find it. Okay, in this problem. Now what do? Now you bring back the external loading. Okay, you bring back the external loading. And consider all the internal deformations. Internal deformations means I am asking you to determine this U. So tell me, for this particular problem, what are the internal deformations going to consist of? In response, so suppose I am asking you to reconsider this 10 kilonewton force which I had in my first step removed. Now I am asking you to bring that back, and when you bring this back, what is the kind of deformation this 10 kilonewton force is going to induce in this AB bar or this AB beam?
So the point D moves down.
Point D moves down, but I am asking in general all over this AB, what is the kind of deformation? So this AB is kind of deflecting downward, and that kind of deflecting downward is what? It is just bending. So you have the generation of some deflections and slopes all along this AB, and that will be given, that slope will be given by M by EI. Okay. There will also be some kind of a deformation in this segment CD. What is that? That is the axial deformation, which you have studied in your first year basic engineering mechanics. Okay, so given a force at the ends of a two force member, you have basically an elongation of the amount of PL by AE, PL or whatever, FL by AE, where F is the force in the two force member and L is the length and A is the area, of course. Okay, so this you now have a recipe of obtaining. Okay, so it's like this. The right hand side will be divided into the AB part and the CD part. Furthermore, the AB part will be divided into two segments. The BD part, where you have the moment associated with just this 10 kilonewton, and this AD part, where you will have the moment associated with the whatever the reaction force is here at the point D, together with the force at 10 kilonewton. All right. Now you tell me, okay, before you jump into solving this problem, think for a minute. Okay, just think for a few seconds. What are we trying to do here? You see, in the first step, like it seems like a lot of work, right? That's why I'm going to discuss this. It seems like a lot of work. You see, delta P we have applied, and then we are obtaining these various internal forces. Now, okay, we are no longer considering delta P, we are bringing back 10 kilonewton. Now, in response to this 10 kilonewton also, we are solving another problem. Now, these energy methods were supposed to make our life harder. And instead of that, it appears now that instead of solving one problem, we'll have to solve the same structure for two different forces. So is it really that bad? Actually, it is not that bad, because you see, in the first step, you had applied 10 delta P equal to 1 in the same direction that this 10 kilonewton force was applied. So if delta P equal to 1 generates certain forces here and certain force here in this CD of some magnitude, then do you not think that when you apply 10 kilonewton, all those forces and moments and whatever this axial force here, it will just be a multiplying factor of 10 of whatever the previous things were? Think about it for a few seconds. Tell me.
Yes, sir.
Okay, so you really don't have to actually, in terms of actual work, you do not have to, or actual effort that you have to do to solve this problem. It's not that you have to solve this delta P and then completely forget about it, then do this 10 kilonewton force. It's not like that. Once you have put in some effort, you can exploit that effort to quickly obtain the forces, the moments for the next part of the problem, that is corresponding to this 10 kilonewton. Now you just write like this, that 1 into delta, so this delta P is equal to 1, this delta is equal to delta, that is the deflection at the point B. And on the right hand side, what you are going to do is you are going to consider first the part associated with AB and then the part associated with CD. But this part AB, that itself is going to consist of so from, I'm writing like this, okay, I hope you will understand. So from B to D, and then it will be from D to A, and then this CD part, you tell me what is it going to be? It is simply going to be, so I want you to write an expression like this. Okay, so this delta F is in response to this delta P. Okay, so let that be some delta F CD. But what about this U? This U will be whatever the value you have here, it will be 10 times that value. Okay, because this is generated in this member CD corresponding to the 1 kilonewton magnitude of delta P. But when you are applying 10 kilonewton, I'm going to use this FL by AE thing, okay, for this. Okay, for this part, FL by AE. So what I'm saying is that this F in the CD is actually just the 10 times of whatever this thing is going to be. Okay, and this is the axial deformation. So I hope, this is not very straightforward, but once you get the hang of this, you will see that I mean, it has certain benefits. I'm not saying that it is necessarily easier than the Castigliano's theorem. Okay, I personally always think that the Castigliano's theorem is a much easier way of doing things. But the advantage of this principle of virtual work is that, and why you should learn it, is that in those cases where this kind of a structure is not going to be made of these linear elastic materials. For example, it is not made of steel, rather it is made of some kind of novel polymeric material. Then you simply cannot use Castigliano's theorem. You have to fall back on the principle of virtual work. Okay, so now that I've discussed all of these things, you tell me if you have any question, any nagging doubt or anything, you just ask. Think about it for a few seconds and then ask me. Anything, okay? No question is stupid. And these are not very straightforward things. I admit that. All right, first of all, you tell me, okay, maybe if I just ask you in this abstract fashion, nothing will be clear. You just tell me for this BD part. Okay, for this BD part, let me go to this new page and tell me. Just for this integration for this BD part. Okay. What should I write? You consider this structure together with the 10 kilonewton force and tell me.
Sir, integral MD theta.
Integral MD theta. Okay, integral MD theta. Fine. Okay, so we have to go from B to D. So D theta we have already established that this is going to be MDX divided by EI. Okay, we have discussed that in that extra video lecture that I had prepared. And this is this is 0 to 2 meters, so I can write that. What is this M? You look at this picture and tell me. Small m, yes, small m is the moment that is generated at any cut section between B and D. So if you take any cut section here, this is the moment. There will be some shear force also, but we are not interested in that. So what is this M?
Sir, M equals to minus delta px.
Right. M equal to minus delta px. So for actual calculation, this is just minus x. Okay. So because delta p is equal to 1 kilonewton. So this answer is going to be in terms of the factor of 10 to the power 3 because we are considering the kilonewton thing. Okay. What is this capital M?
Sir, 10 times small m.
Yes. So this is minus x, this m is minus x. Capital M is just the moment associated with the 10 kilonewton force. So if for delta p equal to 1 you have minus x, for the force equal to 10 kilonewton you will have minus 10x. That's it. So when I said it in words, it sounded probably a little bit too complicated. But now when you actually do the algebra, it's not that. Okay, I am not going to do the part for the AD because for that I'll first have to determine what is the force in the CD, but you know how to do that. Okay, so do the actual calculation and see. Once you have done all these steps, I would encourage you to also check. Okay, so compare the above solution So compare the above solution based on the principle of virtual work with the solution based on Castigliano's theorem. Please note that Castigliano's theorem is not like a magic bullet. Okay, for the application of the Castigliano's theorem also, you will have to uh, determine the force in this member CD, and then you will have to determine the moment all along this member BA. You will also have to consider the axial deformation of it. Okay, but like there was a subdivision between the virtual forces and the real forces and all those things, that extra apparent complication will not be there in the Castigliano's theorem. So if you manage to determine the moment all along the member BA and you determine the force CD, then immediately you can write down the total strain energy, and then by partially differentiating that with the force P equal to 10 kilonewton, you can determine the answer. Okay, so that's it. Okay, let me go to this next problem. This is a fairly straightforward problem, but
Sir, excuse me, sir.
yes.
Sir, in the above problem,
Yes.
sir, can you please go ahead?
Yeah.
Sir, towards the question. Yeah, sir, here we can find the deflection of point B with respect to D, and we can simply use the deflection of rod C. I mean, we can add reflection of rod CD to it.
So you want to actually consider this AD part separately and this BD part separately.
So what I want to do is that let me assume that the part BD is some different problem,
Okay.
and find different.
I think I lost your voice.
So now is it fine?
Yeah. Tell me.
So what I want to do is that to find deflection of point B with respect to point D.
Okay.
It would be simply like a cantilever beam.
Like a PL cube by 3I.
Yes, sir. For
Okay.
that, I will add the deflection of rod CD due to its axial load.
But that won't work unless you also consider the deflection of the member AD. If you just add to it the deflection of CD, you are going to miss out on the information which is present here due to the deflection of AD. Because see, the deflection of point D, it is not just due to this extension. Is it not?
Yes, sir.
This part is also contributing. In fact, it is kind of resisting. You see, if without any resistance, if you had just extended this, the amount of deflection it would have had, it would be different compared to the case when this point D, it is attached to this AD, because this AD is acting then like a kind of resistance to its extension, right? So
Yes, sir.
so effectively you actually have to, I mean, you cannot bypass the difficulty of having to consider the segment DA. All right, because that is very much part of the original structure, and the information that is conveyed by that has to be taken into account in the calculation of the final answer. Otherwise, you are going to miss out on a very important portion of the answer. I mean, the final answer that we'll get will be a partial answer, and of course, that's going to be wrong. Okay.
Yes, sir. Got it.
All right. So for this next problem, what we have is a shaft BC this is a shaft BC. It has a circular cross section, as you can see here. Some diameter is here. This shaft BC, it is welded to the beam AB. So the beam AB is a beam. And this AB has a rectangular cross section, 70 mm by 50 mm. Now a torque T naught equal to 2.5 kilonewton meter. Please note that this I've mistyped it. Okay, there's a typo here. There's a gap here between M and is applied at C as shown. We are supposed to determine the rotation of the end C. So both the shaft and the beam are made of steel. Nice. You tell me what is happening here. What do I have to do? You can directly consider the Castigliano's theorem. Tell me just from a mechanical idea, what is actually happening here? Describe to me the problem. You don't have to tell me any formulas or anything. We are applying a torque here. So this, when you apply a torque on a shaft, it has a tendency to rotate. No big deal. But the end B of this shaft, it is not actually welded to a rigid wall. Instead, it is attached to this beam. So we know that this beam is a deformable member that will also have a tendency to deflect up and down, whatever. So in reality, what is happening? So can we perhaps draw this diagram in a slightly three-dimensional kind of way, like this? So this is our beam, and we have the shaft here. So shaft is like this. I think somebody's microphone is unmuted. It's creating some background noise. If you can mute yourself, please check yourself. Okay. So we have this kind of a structure, right? And it is given that a torque T naught is being applied like this at this end. So probably this is a better picture, and you note that we have a wall here. Okay, this is the wall. That is a rigid wall. No problem there. So this shaft is going to rotate about its own longitudinal axis, no doubt about this. But what, if any, is the extra effect of this T naught?
That will cause the bending
creates bending moment to the rectangular rod.
Yes. So if you consider this beam, then this T naught, which is, I mean, if you're considering the shaft, this T naught is like a torque. But this same T naught, if you consider its effect being transmitted here, then it is acting like a bending moment. In fact, if you consider the x-axis like this, the y-axis like this, and the z-axis like this, and you look at it from the xy plane, then it's going to look like this. Okay, and then this torque will actually look like this, which is just like a bending moment. Okay, so till now we have mostly been considering the application of forces, and the one combined problem that, or the one problem on combined loading that we did yesterday, if I just refer back to this problem, okay, that was through the application of a force. It created a bending in this segment AB, and it created some torsion in this segment BC in addition to the bending moment. So in that exact same spirit, I wanted to discuss another situation where the driver of the overall deformation is not just a force, rather a torque. So you can see the effect on the various parts. Okay, once you get a clear-cut idea of the actual mechanical situation, if you're just a little bit careful with the algebra and the calculation, you can get your answer. Okay, but this initial conceptual idea of the problem, I think that is a very valuable thing. Without it, you cannot even start any problem. All right, so now in the 15 minutes that's remaining, I want to discuss a very special problem. Not this one, okay, the next one, this one. And I hope the students who did BEM in their spring semester will remember this as the absolute last problem of the last tutorial sheet sheet that was circulated. Okay, I think in my section some students were there who are currently here. I think students like, I think I remember Manish Singh was present in that class, and I think probably Swastika was also present. So do you guys remember this problem? The autumn guys did not have this. You did not have a tutorial sheet on indeterminate structures, I think. But the spring guys did have this, and they had a very interesting problem in the final exam also on a tensegrity structure. So this problem is certainly easier than the tensegrity structure problem. So what we have here is just 3 bars, 3 members, pin jointed, okay, everywhere, and this is a statically indeterminate problem, and we are supposed to find out the force in the member BC. Okay, so tell me how I should proceed. I really appreciate it if some of the students from autumn semester actually tell me how to proceed.
So it's like the deflection at the point B would be same. I mean, it will be always in the same intersection point, even there is an elongation in all the ways.
Yes, elongation will be the same, of course. I mean, if you're even if you're considering B as a part of BD, or B as a part of B, or B as a part of BC, it's going to be the same elongation. I think you're referring to that.
Yes, sir.
But that's actually a complicated condition to impose. Can you see something probably a little bit simpler? Okay, suppose I tell you that this BC member is not there. Can you solve this problem then? Can you find out all the forces that, I mean, in this BD and B? If BC is not there, suppose, imagine BC is not there, then you can find out the forces in BD and B. I mean, it's the easiest thing to do in the world. Is it not?
Simple.
Very simple. Well, you don't even have to come to, in your first year plus 2, you can do this. Okay, but BC is there. Okay, that is creating all the problem. So we have learned now in statically indeterminate problems, whatever is creating the problem, you remove that initially. Okay, you commit a crime by changing the problem, and then you take the punishment for that crime. Okay, I think I'm saying the same kind of words which I used in spring BEM. Anyway, so we will do that. Okay, so it's like this. Original problem is like this, that we have this ceiling from which we have can't draw anything properly. Okay, something like that, and then we have this force P. Please note that this is pin jointed. Okay, all right. So what I'm saying now is that remove this thing. So I mean, remove the connection. if you remove the connection, what do you do when you remove that connection? So unlike
Replace it
what,
with a force.
yes, we have to consider a force. So this is in the spirit of things which uh, which we have been in which we have been talking for the earlier statically indeterminate problems. So let me just quickly shift back or switch back to that page where we had considered a statically indeterminate problem, and let me just highlight to you the similarity in the idea with which I'm going to proceed. You see, we had this statically indeterminate problem, and our objective here was to determine the reaction force here. So we removed this thing and replaced this one through this equivalent RB. And then what we did was we kind of pretended that we are going to determine the deflection in response to this RB, and we did the exact kind of steps which we always do when applying the Castigliano's theorem, that we did we took the strain energy associated with bending of the overall problem, and then we just did a first partial derivative with respect to the force, to the point force, which is this RB itself. And then whatever we obtain this thing in terms of this unknown RB, but then we cleverly impose the condition that okay, we have pretended to find a deflection, but actually we know the deflection there, it is actually equal to 0. So from that condition imposed on the deflection, we went on to determine the RB. So this is the overall spirit in which we proceeded with the statically indeterminate problem. Here in this one, here exact same idea. Okay, so this BC member is creating the problem. We will remove the BC the connection at C and replace that by a force at C. Okay, so let me do that. And I'll just write a force. This is RC or what yeah, C. So let me just name these things. Okay, this is B, this is D, this is C, this is E. So here it is RC, pointing vertically upward. All right, so for this problem we can very well write down the total strain energy, and that one will of course involve this RC, which is not known. And ultimately the condition that we are going to impose is that, or the problem that we are going to pretend to solve is that we will pretend that we wish to find out the deflection at this point C, but then we will say that no, we already know this thing, so from that condition we will be able to determine RC. Okay, so this is the overall plan. Let us implement it. So first of all, however, we have to do one small housekeeping kind of thing, in the sense that we have to take care of the forces which are present here, because without the knowledge of the forces in these two members, we are not going to be able to write down the expression for the strain energy for this BD and the BE members. Okay, and overall the situation is very nice and symmetric. So if we know what is happening to BD, we also know what is happening to BE. So that way it is good. So very quickly we are going to write down the expressions of the forces in BD and BE. So let those forces be this thing, let's call it F0. And what we are going to do in order to determine those forces, well, when I say determine, it is quote unquote determine. We are not really going to determine. It's a statically indeterminate problem. Using statics we cannot really determine, but we'll just going to write down some expression in terms of RC. So let's see what is it. So I will consider the free body diagram of this pin joint B. Downward force P, two oblique forces. Let this be F naught. Let this be F naught. And this one, this force, what is it going to be? Well, you can clearly see for yourself that if I isolate the member BC, its free body diagram will just look like this. This is RC here. This is RC here. Let me reduce the length of this. This is RC here, and this RC is being exerted on the member BC by this pin. Correspondingly, this member BC is also going to pull on this pin by a force RC. So it is like this. So now it is very easy to write down this expression because these angles are already given to us. So tell me, what is it quickly?
Sir, 2 times F naught cos phi plus RC is equal to P.
Very good. But see, I don't want to just leave it like this. My objective here is to express this F naught in terms of this RC. So I will just rearrange it quickly like this. All right. Next, what I'm going to do is start writing the expression for this delta C. So capital U is the total strain energy of the overall structure. That I have to partially derive with respect to RC. And now this is del U BD del RC plus del U BE del RC plus del U BC del RC. You tell me, what is the expression of this UBD? What is UBD? So consider only the axial stretch. What is the axial force in this member BD? It is nothing but F naught. So what is it? F naught LBD, rather F naught square LBD divided by?
Sir, of sigma.
You don't have to give me the final expression, this intermediate expression only I was asking. Okay, so basically I'm using the expression for the strain energy associated with axial stretch, which is just like P square L by twice AE. So here I am writing the appropriate lengths LBD and LBE. Now please note that this LBD is equal to LBE is equal to how much? This BC length is given as small l. Okay, so LBD is equal to LBE is equal to L by cos phi. Is it not? L by cos phi. And F naught we have already obtained in terms of this RC. So these two expressions are actually the same. So in the next step, I'm going to write this as just the twice of one of them. And tell me, what is the expression of this BC, UBC?
RC square.
Yeah.
Small l by 2.
RC squared L by twice AE. Okay. So job is basically done. You just have to complete the algebra. So this and this are the same. So this is I am noticing that I have practically run out of time. So officially I am ending the class here. You can go to your next class nicely, no problem. I'll just continue recording for 2-3 more minutes to just finish up with the remaining steps. So thank you very much, everyone. We may or may not meet on Monday. Nevertheless, we'll continue having our communication through MS Teams. But anyway, just officially, I'm telling you all the very best for your test next week. And those who are going to sit for compensatory test also, all the very best for that. Okay, so you can all leave. I'll just continue recording for a few more minutes to finish it up. Thank you very much, everyone. It has been a wonderful experience teaching you. Thank you.
Thank you, sir.
Thank you.
Sir, if possible, stop this recording and record another.
No, let it run for a few more minutes. Just a few more minutes.
Okay.
Yeah.
Thank you.
Thank you.
Thank you, sir.
Thank you. So I'm using the expression of this f naught equal to p minus rc by twice cos phi here, and then I'm going to just use this del f naught del rc, that is going to be equal to minus 1 by twice cos phi. This is what I'm going to use here. So all right, so this is the expression for the delta C. But we know that delta C is equal to 0. Therefore, this entire expression that we have just obtained, that is going to be equal to 0. So please note that this f naught is still remaining here, and this f naught has to be replaced by this p minus rc. Furthermore, there is this minus 1 here. So what I can do is I'll just skip a step here. I'll transpose it to the right hand side and remove this minus. And then I'll just please also note that this L cancels with this L, this AE cancels with this AE, so it becomes considerably simpler. And this 2 cancels with this 2 also. So what we have here is this P minus RC by twice cos cube phi is equal to RC, and if you simplify from here, you are going to end up with RC is equal to P divided by 1 plus 2 cos cube phi. So that's the answer. So all right, thank you very much everyone. I'll stop the recording. There were some messages here. Okay, thank you everyone.